Let's talk about normal distributions. A normal distribution looks like this. Okay, it's centered on our mean, whatever that value may be. And we have a nice gradual smooth decline from our mean down the number line, and we have the same symmetrical, nice, smooth decline moving up the standard, or moving up the number line, right? So that we have a very even, symmetrical, bell-shaped. Sometimes we refer to this as a bell curve because it looks kind of like a bell, right? A nice symmetrical one-peaked distribution. And what that means is that most of our values are right here very close to the mean, right? There aren't a lot of extreme values. Most are very close into this cluster here. We have a few values that are a little bit bigger. We have a few values that are a little bit smaller. We have very few values that are a lot bigger and very few values that are a lot smaller. And we don't have any values out here that are extremes, right? That are so large or so small that we question whether or not they belong to our data. So we have this nice smooth bell-shaped pattern, right? A lot of things in real data fit into a nice curve like this, right? Let's say that we are looking at the height of students, and let's say, for simplicity's sake, that the average student is 5'10", right? So this would be 6 feet, this would be 6'2", 6'4", and we come down here would be 5'8", 5'6", 5'4", and of course we would keep going in both directions there. But what this would mean is that most of our students are pretty close to our mean. We don't have very many students that are quite a bit taller than average, and we have even just a few students that are that are smaller than average, and we don't have very many that are a lot taller than average or that are a lot shorter than average, right? So a lot of things in real world data fit normal curves very well. The power of this is, let's say that we have a student who comes into class and he's 6'6", right? So he's clear over here, and we can say, how far away is that guy from the mean relative to the dispersion of our data? So we can calculate out this distance and make it relative to our distribution and say, look, in our class, 100% of students are shorter than 6'6". So this is an unlikely height. We don't expect students to be that tall. So this is rare. And because it is rare, there is something statistically interesting happening with this individual. Right? If we have another student who comes in and she is 5'9", and so she sits right here, we calculate its relative distance, or her relative distance from the mean relative to the dispersion of the data, and we say, look, that's really not that impressive. At least half of our students are within that distance of the mean. So at least half of our students fall within that distance of the mean. So her height is not really that remarkable. This is a common value, and so statistically, not a whole lot is really happening there that is really interesting, right? So we use a definable normal distribution to get at the commonness or the rarity of a value, and therefore we decide whether or not it is unique and odd and special, or whether it is common and expected and therefore not really a big surprise to us. Okay, let's talk about how we do that in R. Let's use it as an example, the height data in the trees data set, so the height variable inside the trees data set. If we plot that, we see that we have roughly a normal distribution, right? We can see that we have a few trees that are about 60 inches, 60 feet tall, a few trees that are above 90 feet tall, but most of them are about here at about 77, and we have gentle, smooth descending curves on both sides, and it's fairly symmetrical. So let's talk about the four functions that we can use to ask questions of this graph. So the first one is the density function, and this is what you use when you want to find the probability of a specific value. So if I look at that curve again, let me pull up an example of it here. And in this one, all I've done, the thicker dark line is the actual tree data, and this thinner line is a normal distribution superimposed over the top of it with the same mean and the same standard deviation, right? So let's say I want to say, what is the probability that if I go into the forest and I see these trees and I randomly pick a tree, what is the likelihood that that tree will be exactly 80 feet tall? Right? So what is the probability that if I walk into the forest, the trees that I look at will be exactly 80 feet tall? So here's our 80 feet. And what's going to happen here is we're just going to climb up this vertically until we get to this point on our that normal distribution, and then come across. And it will return this probability. So something less than 5%. Okay, so there's a 5% chance essentially that if I walk into the forest and randomly pick a tree, it will be exactly 80 feet tall. All right. So let's take a look at how we do that. The function is d for density and norm because we're looking at normal distributions. And the value that we're testing is 80 feet on a distribution defined by the mean of height and the standard deviation of height. When I run that, we can see that it is just over 5%, right? So there is a 5% chance that if I walk into a forest and I randomly pick a tree, there's a 5% chance that it will be exactly 80 feet tall. Okay, the cumulative probability function is related to that, but this is the probability of a specific value or less. So this is the key here, the part or less. So what that looks like, but I'm not just interested in this value alone, I'm interested in all possible trees that are shorter than that height. So we are now looking at the area under this curve that is less than 80. So in other words, we're asking what percentage of the trees in our forest are less than 80 feet tall. And we do that with the p-norm function. We're going to stick with our 80, and this normal distribution is also defined by the mean of height and the standard deviation of height, right? So if I run, 73. So it turns out in reality, so here we had our 80, 73% of our trees are 80 feet tall or shorter, which leaves 27% are taller than that. Okay, so the key here is that instead of just looking at the specific value and only that value, we're looking at all of this area below this curve, right? Of all of the area below the curve, what percent of it is less than or equal to 80? And in this case, that works out to be 73%. Okay. The next function that we can use is the quantile function, and it's the exact opposite of the cumulative probability function. So here, it's going to return the value of a specified, that's why I was abbreviating it, of a specified probability. So I'm going to supply a probability. So let's say that the function here is qnorm. I'm going to say, what value separates the 75% of the shortest trees from the 25% of the tallest trees? So it's the number that distinguishes 3/4 of the trees as being the shortest, and then the fourth that remains is the largest, right? And again, that is defined by the mean of height and by the standard deviation of height. And that value is 80.29. So what we're doing here is kind of the opposite of what we were doing with the p-norm function. We're saying we're supplying first the value, so 50% is right here where the mean is, right? So 50% is less than the mean and 50% is above the mean. But we're saying I'm supplying the value 75% and it returned back the value of 80. So in essence, you can think of this as though the computer is starting on the right side, sorry, the left side, starting here and moving this way until all of this area equals the amount that you have specified in your question. And in ours, it was 75%. So when we get to the point that 75% of our data is below that line, then we stop, and it returns this value, which in this case was actually 80.29 or something, I think it was. Okay, but you specify the percentage, and it returns the number here, which is the divider between the 75% that you've specified, and then of course the remaining percent in this case is 25. So we use this to ask ourselves, what grade do I have to get to be in the top 10% of my class, right? You would put this in. So in that scenario, this would be a 90, and we would say, to be in the top 10% of trees, you have to be 84 feet tall or taller. Okay. The third one is just a random number generator. So this generates a random set of numbers that are normally distributed. The command there is rnorm, and the first input is, just to keep this simple, let's just say I want 20 numbers drawn from a population that has a mean of 10 and a standard deviation of 3. So if I run this, it will create for me 20 numbers that have a mean of 10, and you can see that most of my numbers here are close to 10, but it has a standard deviation of 3, so my data are going to range from 1 up to 19, right, because that's 3 standard deviations below the mean and 3 standard deviations above the mean. And so you can see that it has randomly created a list of 20 numbers, and that most of those numbers are pretty close to 10. We have a few that are farther away, and we have even fewer still that are quite a bit farther away. But we've created a random number there. So based on a normal distribution, these are the commands that we have that we can use in R. The density function, which is dnorm, the cumulative probability function, which is pnorm, the quantile function, which is qnorm, and the random function, which is rnorm.